Hey guys, we're going to go ahead and do a couple examples of our World Series. Hopefully you've already seen the World Series Basics and or the Geometric Series, the World Geometric Series Basics. So I'm going to assume you've already seen that or you were in class, and we should be able to attack a problem like this now. All right. So at first glance, it doesn't really look like anything special. There's nothing I can really, it doesn't look like the geometric ones from before, and there's nothing fancy I seem to be able to do with this. So maybe it's a good idea to just actually list out, a couple terms just to get a feel for what this thing looks like. Okay, so if I list out a couple terms, my first term, if n is 1, this becomes 1. This becomes 2 to the 2, which is 4. Plus, when n is 2, let's see, this becomes 2 to the 4, right? 2 to the 4, so that's 16 times 3 times 3 to the 1 minus 2, so that's 1/3. So this would be 16/3. Okay, and let's go one more. If I go n is 3, this is 2 to the 6th. All right, so what's that? 64. And at 3, I'm at negative 2 now, so that's 1 over 9. So that's 64 over 9, etc., etc. And then I'll just put a sub n. Okay, so these are my terms. So, the whole point is, to determine if this is going to converge or not. Right now, we really only have a couple of options, and one of those is to see if it's geometric. So I'm looking at this and I'm trying to figure out, is there a common ratio that, gets me from here to here or here to here? So one of the tricks is, if you can't quite see it, is you could always divide. You could divide this term by the term before it and see if it matches what happens when you divide this term by the term before that. And then hopefully you'll see that it does look like I'm multiplying by, 4/3, right? 4/3 times 4 is 16/3. 4/3 times 16/3 is 64/9, etc. So it looks like I do have an R value of 4/3. Unfortunately, in order for this to work, I need an R value that is, an absolute value less than 1. So 4/3 is obviously greater than 1. So this series diverges. Now, let's say you didn't want to list out all these terms and you were just kind of stuck in here. We could manipulate this a little bit to make it look more geometric, because this is a geometric series. It just happens to diverge, right? This is geometric with R equaling 4/3. So if I want to manipulate this, let me just sneak down here real quick. Let's go ahead and rewrite this. 2 to the 2n is the same as, isn't that the same as 4 to the n? Right? So I have 2 squared times 2 to the n. That's 4 to the n. 3 to the 1 minus n. All right, this one's going to be a little tricky. 3 to the 1 minus n, isn't that the same as 3 to the negative n minus 1? Right? Distribute the negative, you'll see you get the same thing. Now, why would I want to do that? Because I want to put this in the denominator, because I know that's where it's going to end up going. So this becomes 4 to the n times 1 over 3 to the n minus 1. I'll clean that up. This becomes 4 to the n over 3 to the n minus 1, and we're close. Obviously, these powers being different doesn't really help me to come up with that common ratio. So you see how this is 4 to the n and this is 3 to the n minus 1? It's almost like this has an extra, an extra term in it to get me all the way up to n instead of n minus 1. I really want the term before this. So if I do this, sorry, that got a little smudgy there. There's nothing there. Okay, if I do this, I can actually pull out a 4. 4 times 4 to the n minus 1 over 3 to the n minus 1. Right? That's the same thing. 4 times 4 to the n minus 1 is 4 to the n. And now you might be able to see it. This becomes 4 times 4/3 to the n minus 1. AR to the n minus 1, right? Isn't our general form this? So sometimes you can just manipulate them and you'll be able to see it. Now here I can see my initial term is 4. Okay, my R value is 4/3, which I got this way by listing them out. But sometimes it's hard to list them out, and sometimes you can't really figure this out that easily. This method actually works nicely, and this is something you really kind of need to be able to do going forward anyway, so it's probably good practice. Okay, so there's one example. And then there was another one that I didn't have time for in class that I wanted to show that looked like this. N equals 1 to infinity, 1 over n times n plus 1. And we're trying to show if this converges or diverges. Okay? Well, unfortunately, this is not geometric. There's no way you're going to get geometric out of this. Again, if we list out a few terms, you'll see. If n is 1, I get 1/2. If n is 2, I get 1/6. Oops, plus this series, right? 1/6. If n is 3, I get 3 times 4, that's 1/12. And let's go one more. 4 times 5, 1/20. Dot, dot, dot. And there you go. I can't just multiply by 1/3 to get here because then it changes each time. So unfortunately, it's not geometric. So there are other kind of tricks we can do. And hopefully when you look at one like this, it might ring a bell. Remember how we were able to manipulate a fraction to make it like smaller fractions? So we basically said 1 over n times n plus 1. Isn't that the same as this? Right? I want to figure out the little pieces for this. So just a little bit of what seems like integration by parts. I'm sorry, partial fractions. We're not actually integrating. We're just using the partial fraction aspect of it. Okay? So this becomes a(n plus a plus bn, and that has to equal 1. So I know my a(n) and bn, right? a(n) plus bn must equal 0, and a must equal 1. Well, that's convenient, right? So a plus b equals 0. 1 plus b equals 0, so b equals -1. So now I can rewrite this. I'll rewrite it down here. This also becomes, a was 1, so 1 over n plus, I'm sorry, not plus. There is plus. It's plus -1 over n plus 1, right? But what I meant to write, I just meant to subtract. So this becomes 1 over n minus 1 over n plus 1. That's what I wanted to write. And that's something we can actually manipulate a little bit using a technique called telescoping, which is going to look kind of cool. It looks like exactly how it sounds. Watch this. Let me just get some extra space down here. So this is what I'm looking at right here. Okay, so just imagine that. So let's list out a few terms in that form. Okay, so my first term, n equals 1, is going to be 1 minus 1/2, right? Which matches. We said it was going to be 1/2, right? My second term is going to be, if n is, let's say 2, right? I have 1/2 minus 1/3. Well, what's 1/2 minus 1/3? 3/6 minus 2/6 is 1/6. So I'm not changing anything. I'm just rewriting it. And I'm going to write it in a very convenient way, and that's why we're doing this. Let's go to the next one. This is going to be 1/3 minus 1/4. Maybe you can start to see the pattern. Okay, let's do one more. 1/4 minus 1/5, right? 1/5 plus dot 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 1 over n minus 1 over n plus 1. All right, the whole reason I'm writing it out the long way there is because hopefully you can start to see this cancels with that, this cancels with that, this cancels with that. This is going to cancel with, whatever. Eventually there's going to be a 1/5, the next one. And then eventually, this one's going to cancel with the one right before it, and all you're actually left with are these two items. So this is the equivalent of 1 minus 1 over n plus 1. All those middle terms end up kind of canceling out. And that I can take the limit of. The limit as n goes to infinity for that, of 1 minus 1 over n plus 1, is 1. So my actual series does converge, and it converges to 1. You're certainly welcome to graph it and use the little trick with the cumulative sum technique, and you'll be able to see that it does actually add up to 1. Okay, so that was just another example that I run out of time, but if you follow the steps and you use our little partial fraction trick, it's a neat little way to use this new technique called telescoping. It's not very common, telescoping. It's not very common, but you can kind of see it. It kind of works like a telescope. Like, you can stretch it all out, and then you can fold it back together. And by folding it back together, you just end up with the first term and that last term. Okay, so just a couple additional examples. Just take a look and let me know if you have any questions, and I will see you guys later.